to start. And the first talk is will be given by Cristina Lazzeroni on rare decays of strength, charm, and beauty hadrons. And Cristina, I will indicate you by voice when you will be at 5 minutes left, if it's fine with you.
Good morning, thank you. So I will share my screen. Okay, so good morning. And yes, I'm going to show some rare decays of strange, charm, and beauty meson. So first of all, I'd like to start with saying that the flavor is a special laboratory acting like a sort of magnifying lens on especially on processes that are sensitive to loop, so higher order processes, because they're very sensitive to the presence of new physics. Besides, the rare processes are clearly suppressed in the standard model, and so they have a chance to show new interactions that can give major contributions. And also these new interactions can also have different symmetries with respect to the standard model. But overall, it's extremely important to over-constraining the new interactions and coupling in the entire quark sector, strange, charm, and beauty, to understand their origin and fully pin down their characteristics. So in my talk, I will try not to separate charm, strange, charm, and beauty, but put them a bit together in an idea just to see how they could be perhaps used to constrain a full picture. So in general, there are two strategies to do so. The first one is to search for deviations with respect to standard model predictions for observables that have a different degree of sensitivity to beyond the standard model phenomena, that are ideally only mildly sensitive or almost no sensitive to hadronic corrections, and they are accessible experimentally. For those, it's important to have precision, both in experiment and theory, to make this investigation the most effective. Examples of this have lepton universality B anomalies, which were the subject of the talk of Lucia's yesterday, and some specific flavor change in neutral current process, that some of which I will show in my talk. The second strategy is to search for processes forbidden by accidental symmetry of the standard model. And these are very clean probes of new physics, because any signal is clearly a sign of new physics effect. And so lepton flavor violation and lepton number violation are examples of this. And so in this talk, I will show some recent results with some personal choices. I will start with the channels that are very clean theoretically from NA62, COTO, Bell 2, and LACB. I will then move to two channels from LACB and Bell, where the theory uncertainty is a little worse. And then I will show two channels from LACB and NA62, where we go beyond the branch ratio and we look at angular analysis and form factor measurements. And finally, I will briefly show three examples of forbidden processes from NA62 and Bell. For details of all of these measurements, clearly you should see the dedicated talks in plenary or parallel sessions. So first of all, I'm going to start with the golden channels, so those which are very clean theoretically. And the first one I'm going to show is the K 2 pi nu bar. These are flavor change in neutral current high order processes with the highest CKM suppression. And the point of this are basically free from hadronic uncertainty, and they benefit from an exceptional standard model precision. They're also sensitive to new physics in a variety of beyond the standard model scenarios. But on a general term, if we look at how this process could be mediated at 3 level by new particle, for example, at Z prime, you can see that they're sensitive to very high energy scale of the order of 2000 TeV. So these decays have been a long history of both experimental searches and theoretical calculations over many years, as you can see from this plot, spanning from 1960 to now. And it's in this context that we have recent results from the Na62 and Koto experiments, respectively, for the charge and the neutral channel. So the Na62 experiment looked at 2016 and 2017 data and found one candidate in 2016 and two candidates in 2017 data. And so combining the two put a limit on the Branchy ratio of less than 1.78 at 10 to the minus 10 and 90% confidence level. And as you can see from the plot in the bottom right, this is already was an improvement with respect to previous measurements and started to constrain the phase space for new physics with respect to the standard model that you see in the plot as a green cross. So then the Na62 experiment also took data in 2018, which a much larger sample, and in 2018 found 17 candidates. As you see in this plot, which is shows the missing mass squared versus the momentum of the pi plus. And basically with then combining the two samples together, 16, 17, 18, there are 20 observed events, which considering that the data expected signal and expected background features very well with the observation, can be put a measurement of the Branchy ratio of 10.6, 10 to the minus 11, a 68% confidence level with a 3.4 sigma significance. And this is indeed the most precise determination of this decay rate to date. And so just to put a little bit in context what that may mean, if we look at the scatter plot of the k plus 2 pi plus nu bar versus the k long 2 pi 0 nu bar, we can see that the standard model is the cross, and basically you can see that different new physics model foresee different correlations between the two channels. So we go from the green band, which is minimum flavor violation models, to the blue area, which are models with new flavor violating interactions with either in the left-handed or right-handed couplings, and the red, which is models without the above constraint. So clearly the correlation is very much model dependent. Besides, the kaon sector can also correlate to the B sector, again, in a somehow model independent way. So if we look at for example, these papers on the effective field theory, with the assumptions that the new interactions responsible for the lepton flavor universality violation in the B sector couple mainly to the third generation left-handed fermion, we note that only these K decays are sensitive to the third generation leptons because of the tau neutrinos. And so one can find correlations between for example, the K plus 2 pi plus nu bar and the analogous B channels as a function of the mixing parameters defining the flavor base and the relative strengths of the new physics interactions, which are these two plots on the bottom. And so clearly the correlations is model dependent. And again, I reiterate my point that it's very important to look at the global pictures when measurements are available to try to constrain new physics in a general sense. So then the Koto experiment is looking at the pi 0 nu bar, and from 2015 data with a single event sensitivity of 1.3 10 to the minus 9 and 0.42 predictive background, they found 0 observed event in the signal box that you see here in the scatter plot between the vertex, reconstructed vertex of the pi 0 and the pi 0 transverse momentum. And so they place a limit, a 90% confidence level of less than 3 × 10⁻⁹. This is the current best limit. On the 2016-2018 data, they have a better sensitivity of 7 × 10⁻⁻10, but 3 events appeared in the signal region with 1.22 background event. And so the prospect for the Koto experiment is that in now basically there is a shutdown, and there will be a power supply upgrade of the main ring, and so the power, the beam power will go from 64 to 100 kilowatt, and also there is a DAC upgrade with the possibility to have a 4 times rate able to be collected, which will allow to also collect events such like K long to pi0 plus or minus. And then from 2022 to 2025, Koto will collect 11 more times data to get a projected single event sensitivity of the order of 10 to the minus 11 by 2026, which is indeed the Branchy ratio as predicted by the standard model. Okay, so again, what does it mean? So the new measurements from run 1 of Na62, you see here as a pink band that is already consistent with the standard model at present, but substantially shrink the uncertainty. And so part of the parameter space is already ruled out, as you see on the plot on the bottom right. The next target is to reach at least 3 times in precision to match the theoretical uncertainty by LS3 of the order of 10% precision. Now, in models of leptoquark, for example, that recent publication, there is the plot on the bottom left. You can see that the correlation in this model is expected between the charge and the neutral channel. You see also that there is already some sort of exclusion for extreme values for the measurement of Na62 as it is. But you see the dot of the standard model has around a little circle, and that little circle is the predicted precision of experiment of high intensity K-on experiments in the future. So then they will be constraining much more. So the next golden channel is the equivalent of the B, so B plus to K plus nu bar. This is a flavor change in neutral current process, again with very high suppression and a very accurate theoretical prediction in the standard model. The decay is not observed yet, and there is a new result from Bell 2 with 633 inverse femtobarn of data from 19 and 20 years. These decays, it's basically complementary to the search of new physics in the B anomalies, and many beyond the standard model models can be constrained. These decays, for example, again, dark matter or leptoquarks. So previously the searches were done with exclusive tagging, either hadronic or semi-leptonics, while now the analysis proceeds with an inclusive tagging that gives a much higher signal efficiency. And for details, you can see the parallel talks of Bell 2. But the point I want to make is that that allows to set an upper limit because no significant signal is observed. And while the measurement is not very constraining at the moment, but the new technique of inclusive tagging is very promising, and there is much more data of 213 events femtobarn, and more channels will be added. So this is very promising, and we expect 400 inverse femtobarn for the summer of 2022 with a precision of the order of 0.5 10 to the minus 5. And you see that in models with R2 and S3 leptoquark, again, there is a correlation between this channel and the lepton flavor violation channels. Okay, so then the next channels, which is very clean theoretically, is the B to mu mu channels. which are also extremely rare and helicity suppressed. And basically, they're very clean theoretically, as you can see, dominated by a parametric uncertainty. In the summer of 2020, the LAC experiment combined all the measurements in this scatter plot of BS to mu mu versus B to mu mu, where you can see the standard model in red, and the all signals combined curves are the black lines. Then there is recently a new measurements from LACB with the full statistics on 9 invariance femtobar, where also the channel BS to mu mu gamma has been added. And so we have new limits. Well, the first limit on BS to mu mu gamma of less than 2 × 10⁻⁹, and new limit on BS and B0, which you see in the updated scatter plot for the 68 contour, 95 and 99 confidence level contour, and the standard model again in red. And again, the small comment that I want to make is that, again, in the standard model, there is a recent paper that highlights the correlation between Xiaoyan and B sector. And here the Branchy ratios in this paper are written as a function of the CKM and input parameters to eliminate the dependence on BCB. And in this plot, you can see the correlation as a function of the angle gamma. And this is important because in coming years, the LACB, Bell, and NA62 experiment will all improve precision. And so this indeed can be tested. Now I go to other rare decays. And so the first one that I want to look at is from LACB, B in 4 muons. And this again is a very rare process when it's considered non-resonant, with Branchy ratio of the order of 10⁻⁻⁻, 10⁻⁻11. Many standard model extension give contribution orders of magnitude larger. And this is an analysis from LACB from the full run 1 and 2 statistics of 9 inverse femtobonds, searching for non-resonance decays, for decays mediated by axions with mass of around 1 mGeV, and with decays with 1 resonance J psi. And there is basically one looks for a peak in the 4 muon mass window. And so no excess is found above the background expectation, so limit are set and 95% confidence levels. And so a set of 6 limits is set, which include the lowest limit ever achieved by LACB, the first search of B2AA with the mass of the axion of 1 GeV, and the first limit for the decay of BS to J psi mu mu. So the next that I want to show is the Bell decay. Again, it's a flavor changing neutral current, highly suppressed in the standard model, with the Branchy ratio of the order 10⁻⁷. It's sensitive to new physics, where the effect can reach of the order of 10⁻⁴. And basically, this proceeds with the B-tag reconstruction in exclusive B0 decays, using neural letter accurate, where the signal is reconstructed with 4 charge tracks, the mass of the tau pairs, and the missing mass squares. And so the limit is it's done doing a bin maximum likelihood to the extra calorimeter energy, which is the total energy of the neutral clusters in the calorimeter not associated with the B tag or the B signal. And so it's they find 4.9 ± 6 events, and so an upper limit is placed on 90% confidence level. And again, this is the first experimental limit on this decay, and there basically models, for example, leptoquarks U1 models, there is a correlation between K tau tau and deviation in the standard model of RD star. And so here you see in orange models with no right-handed current, in purple with maximum right-handed currents. And so you can see that it is very important to pin down basically in multiple ways these possible new physics models with as many channels as possible. So now I proceed to two more channels beyond the standard. Beyond the standard model. So the first one is the charm decay, and rare charm decays give access to orthogonal coupling that also help to understand the flavor structure of new physics. They're sensitive to flavor changing neutral current transitions, and the Branchy ratio, the specific Branchy ratio to D to pi pi mu mu and kk mu mu are in fact dominated by long distance contributions, but one can exploit symmetries to look for clean standard model null tests in the angular distributions. So the first observation of these channels was done by LCB with 2 inverse femtobarn. And the rate is compatible with the standard model prediction. And now there is a new analysis performed with 9 inverse femtobars. These are the rarest charm decays observed to date.
5 minutes.
Yes. So this differential decay rate can be expressed as a function of the angular coefficients I. The coefficients are measured integrating out the hadronic system, and they are separately measured for D0 and D0 bar, and then the flavored average SI and CP asymmetry AI are calculated and measured in Q square bins, where Q square is the invariant mass of the muon pairs. And so the standard model null tests are S5, the average of S5, 6, and 7, and A2 to 9. And so, for example, we can see the SI here, and the analysis is dominated by the statistics, but all variables are in agreement with the standard model predictions. And this is the first full angular analysis in the rare charm decay ever performed. The second decay that I want to talk about is again a flavor changing neutral current decays with long distance contribution mediated by photon exchange. This is K plus to pi plus mu mu. This is sensitive to new physics, and in fact, together with the electron channel, test the lepton flavor universality. The NA62 measured this based on 2.8 10 to the 4 candidates from run 1, and the model-dependent Branchy ratio of 9.27 10 to the minus 8 is extracted together with the form factors A plus and B plus. In fact, the form factors are extracted from the fitted from the Z spectrum, where Z is the mass mu mu squared normalized to the mass of the kaon, and A and B parameter form factors are extracted, and a paper is in preparation. And then, as I said, putting together the kaon, the muon, and the electron channel, one can perform lepton universality tests, which are complementary to the B sector. And finally, a whistle through to lepton number, lepton flavor violation channels. So the first one is the K plus the pi minus pi 0 E plus C plus. This is the first search of this mode. This channel is possible with via neutrino mixing in the standard model with a Branchy ratio of the order of 10 to the minus 50. So any signal that is observable is a clear signal of new physics, and the new limits has been prepared of less than 8.5 10 to the minus 10 and 90% confidence level. The next channels are K plus T pi mu electron with various combination of charges, and these are sensitive, for example, of leptoquark models. And again, the new limits have been produced by NA62 of less than 4.2 10 to the minus 11 and 6.6 10 to the minus 11 in the pi mu E channels respectively. And finally, the Bell measurements of B to tau lepton. This decay in the standard model can occur in principle again by neutrino mixing, but with a Branchy ratio extremely suppressed 10 to the minus 40. So again, any sign, any measurements of this decay is a clearly sign of new physics and can be mediated by, for example, leptoquarks. So the unbeen extended maximum likelihood fit to the missing masses performed, the limits and 90% confidence level are extracted. And so new limits on B0 to tau mu of less than 1.5, 10 to the minus 5, and B0 to tau E less than 1.6, 10 to the minus 5 are placed. And this is indeed on the tau E, the most stringent limit to date. And again, you can see here in models, for example, leptoquark U1, the pink is the maximum right-handed currents, and you can see a correlation between lepton flavor channels. And so in summary, rare processes are an excellent portal to explore physics beyond the standard model. Specific channels benefit from high suppression, precise standard model theoretical prediction, excellent sensitivity to new physics, and particular experimental handles. The Xiaoyan, the charm, and the beauty experiments worldwide are reaching unprecedented level of sensitivity to beyond the standard model searches, and there are lots of new results and many, many more to come. The correlation between the K, the D, and the B rare decays and the relation with the B anomaly depend on the specific new physics model. And so a global picture is needed to pin down new physics with many precision measurement and precise theory and study the pattern and correlation of new physics models. Thank you.
Thank you, Cristina, for this very nice talk and having managed to keep on time despite the full range of topic, and in particular for the attention you paid for linking the various topics together. So then we have time for questions. If you want to ask a question, please raise your hand. Yes, John Wilson, please.
Hi, you'll have to pardon me, I'm not a flavor physicist, but what is the origin of the Grossman-Near bound and how strict is it?
So it's a nice spin correlation between the two channels, and yeah, it's well, it can be violated in some model of new physics, but in the standard model is a strict bound. So yeah, it's
okay, thank you. So I have a question on the K to pi mu mu and the results from NA62. This is very nice indeed, and I wanted to know if you are planning also to perform some angular analysis, forward backward asymmetry measurement, or maybe I missed the point.
So we are planning to well, so we are angular analysis, maybe. Definitely we are planning to look at the electron channels, that's for sure, but we couldn't so far because we need to re-optimize the trigger in order to increase the sample for the electron channels. It's just that it's a less selective trigger and a higher bandwidth. So we are working on it to be able to collect a higher statistics of the electron channel. The muon channel is easier to collect.
Okay. And what is about, I don't know, can you give us a rough idea of you hoping to have an electron sample of the same size, half the size? Or?
Yes, so we are hoping to have an electron signal, yeah, of the same size, but you know, by LS3. So in the NA62 run 2, we are working on it.
Okay, thank you. So I see Marco Gersavec.
Thanks, Cristina, for the great talk. As you said, in the end, it was a bit of a whistle-stop tour. Could you go to slide 26, please? I think it was just a bit fast, but there's this one bin on the left-hand plot that looks a bit high, but presumably this just gets compensated by the neighboring bins having 0. Is that correct?
Yes, yes.
Yeah, I didn't
Yes.
get to appreciate the axis range. Yeah, okay.
Yes.
Right, that was it.
Yeah, sorry for the whistle through, but
Yeah,
you know,
no,
but many of these are looked in more detail in the parallel talk, indeed.
Thanks a lot.
So, okay, so thank you very much once again. I don't see other questions. Raised hand. So now we will move to the second talk of this morning. So about mixing and CP violation in beauty and charm hadrons by Malcolm John. Malcolm?
Hello, yes, let me just try to share.
So as for Cristina, when you will have 5 minutes left, I will tell you.
Okay. Does that come through?
Yes, we can see your full screen.
Very good. Excellent. Right, okay, good. So it falls to me to give this review to this conference of CP violation mixing in charm and beauty hadrons, and I choose as my cover photo here a painting by the Mancunian painter L.S. Lowry from 1944, showing football being played in Peel Park in Salford in Manchester. Right, so CP violation experiments. So the results here that I will show, there will be, to be honest, most is dominated by LHCb, which is the dedicated heavy flavor experiment at the LHC. But nevertheless, there are a few results that come from Bell and Bell 2, which is an E+E- experiment in Japan, which benefits from creating BB pairs in a known additional state. And there is a small contribution to mention coming from the GPD experiments, Alice and CMS at the LHC, that although have a very large cross-section for producing heavy flavor quarks, does so with a high pileup and thus a more messy environment, as the image on the bottom left might show. So the topics I am covering here, I want to start with talking about the precision measurement of BS mesons, which is a very nice result. Then mainly talk about charm through the first topics, and before going on to talk about beauty towards the end. This, of course, is a plenary talk representing a lot of work, and there's more details to be found in the parallel sessions, which I indicate here. One notable one that I want to draw attention to is the results. There are 2 places which I star with little suns, which benefit enormously with measurements coming from the BESS 3 experiment in China, for which there is a dedicated talk, which I also highlight in the top right. Okay, so yeah, onto the meat of it. So the BS mixing frequency, delta MS, I will refer it to here. So standard formalism is that the mixing occurs with neutral mesons in the case that the mass eigenstate is not aligned with the interaction, the weak interaction eigenstates. And if they're not exactly the same thing, then there can be a time-dependent evolution of the flavor content as these mass eigenstates propagate through space, of which I have a little diagram here on the left. You see that what is originally a BS may stay a BS, or it may, according to a certain probability, transmutate into a BS bar meson before it decays. Some maths follows, and you have a probability for this to occur, which is written out here. And you see that the leading term is the decaying exponential term, which according to the average lifetime for the BS meson. And then it has a hyperbolic term depending upon the difference in the decay widths of the two mass eigenstates, and also a cosine term dependent upon the mass difference, which of course is what the whole measurement is about. So this, although I've brought this in the context of the BS meson, which I show on the left of these illustrations, this mathematics is completely applicable to the other neutral mesons, but the only difference is the difference in the different decay widths and the different mass differences that occurs in the different systems. The BS one is famously the fastest, and you see these very fast oscillations that one expects. The B0 mesons is a slower oscillation, so you only get maybe half an oscillation before the B0 meson decays, and the D0 meson, for very good reason, has very small mixing probability and hardly anything happens, and it's famously very difficult to see this mixing occur. In all of this, you see it from my title at the top here, I refer to having to start with an initial state, and we've got to know what the initial state is, and that's what flavor tagging is all about. It's having to identify what the initial flavor is. So this result, this is a result from LHCb, and it uses BS to DS pi, and this is a Cabebo favored flavor specific final state. So you can, to a very good approximation by neglecting doubly Cabebo suppressed contributions, identify the flavor at the point of decay. You also need the initial flavor, and that's what flavor tagging is about. LHCb, with an enormous amount of work, manages to achieve 6.1% overall performance of the flavor tagging. And just to give some perspective, the Bell and Bell 2, well, let's say Bell 2 have recently studied this for their detector, and they're currently managing 31% as their overall flavor tagging performance. So there you immediately see the benefit coming through of the E plus E minus collider system. So it's a time dependent effect, and let's say there's a cosine in it, and you can clearly see in the data there these clear wiggles up and down, and it's measuring this frequency, gets you the delta ms. And the result, the overall result from LHCb at the moment is this rather precise number at the bottom, the 17.76 radians per second as the mixing frequency, which is obviously an excellent result. The comparison with standard model is not so easy here, because the prediction of the standard model in this process it's not absolutely precise because of the limitations of QCD calculations, but this result is most certainly compatible with the expectation. So on the other hand, the charm mixing is slow. This is completely expected in the standard model because of the elements that play into the expected diagram that drives the oscillation process. So it's very, very hard to see. Though conversely, you can get very good initial state tagging through the use of D-star decays, or indeed semi-leptonic decays, to identify the initial flavor. So the problem is just that it's a very small mixing process. So the trick is to look for the time-dependent change in the ratio of the doubly Cabebo suppressed decays, which previously we ignored in the previous example, compared to the favored rate. And you see on the left-hand side here, we have a small peak divided by a big peak, and that ratio, if that changes over time, is a sign that mixing is occurring. You can see this from the top right, where you have two paths to get to the final state, either going directly over the top of the circle, and that is the suppressed way, or there's a small probability of an oscillation and then a favored decay, and the overall probability of these two is about the same thing, so that when you do the quantum mechanical modular squared operation, you get an interference term, which I write out on this slide. So we have these three terms, The first term is the doubly Cabebo expressed direct rate, which we previously neglected. We have a cosh and cosine term in the middle, which we previously had for the BS case. And now we've got a new term at the end, which is a mixing term. And that is due to the interference between these two paths to get to the final state. With some linear approximations, one gets a ratio expression down at the bottom. That's just a linearization taking the first terms of the trigonometric functions. And you see that it is has a constant term, RD squared, then a term that is linear in the time evolution, and then a third term, which is the quadratic term. So it's dominated by linear effects. And if we look at the data, we see this linear rise going on. And it's a measurement of this linear rise which causes the measurement of or seeing the mixing effect, and absolutely clearly to the eye there is a time-dependent effect which is due to the mixing. Now, in order to extract the mixing parameters, which in the case of charm are usually expressed in terms of dimensionless parameters x and y, which are defined in the middle of the slide there. So they're related to the mass difference and the decay width difference. Directly. The trouble is in order to get hold of the x and y, as you see from the bottom equation, one has to know what the strong phase is, the delta D, that is the strong phase difference, well, the CP conserving phase difference between the two paths, the two decay amplitudes, the doubly Cabebo expressed amplitude and the favored amplitude, that strong difference. And you need to know that in order to be able to extract the x and y from the mixing. And so just taking this this equation here, one would have to get the delta D somehow from either somewhere else, or we've got a multi parameter fit, and it's not completely straightforward to get hold of the x and y. However, if one does some clever stuff by measuring that CP conserving phase difference at an independent machine, so for example BESS3, then one is able to extract the values of x and y fairly directly. And you can be even cleverer, as what happens in this this method, by using k short pi pi. So this is a charge conjugate multi-body state. So you can form a Dalit space, split that Dalit space up into various colored bins, which you see on the left there, and measure the strong phase difference, the CP conserving difference, between one half of the Dalit plot and the other one in the BESS3 dataset. And I refer you to the dedicated talk in the parallel sessions to learn more details of this. But what you get out of it is the delta Ds, which I indicated on the previous slide. So you then split up the LHCb data set, which is an enormous data set, 30 million events, into these various bins, and then look at the time evolution in each one of those bits. Okay, and the plot on the right is the same Dalit space from LHCb with the 30 million events, and you can see very clearly all the various resonance structure. Okay, so bit of formalism here. So this ratio, the W Cabebo suppressed ratio to Cabebo suppressed ratio, which we had 2 slides ago, is now done per bin. So this expression is this R subscript B for bin J and time bin, bin B and time bin J. And it's again a ratio of some sort, and it looks very complicated, but the key thing to try and bring your eye to see is that it has the same structure of a constant term, a linear term, and a quadratic term in time. And we depend upon what is now written here as ZCP, which has got within it the x and y, the mixing parameters we're after, and also everything depends upon XB, which is it's the exponent of the CP conserving phase in each individual bin that's been previously measured. Right. So let's look at the data. So again, we have these time-dependent plots, which we previously had seen when we were just looking at the case of the K-pi final state, which was seemed to be increasing at higher and higher lifetime. This time, the time evolution is done per bin and changes in different directions. And the reason why some go up, some go down is because of the strong phase that has been measured at BESS3. Helpfully, these plots have got red dotted lines on which shows you if what it would be were x. X is related to the mass difference, be 0. So one can see that the blue lines are, once you take everything together, are significantly divergent from an x equals 0 hypothesis. And indeed, the paper from LHCb declares observation of this mass difference as the central point of their paper. So yes, x is non-zero. So this actually has an enormous impact. So the HFLAV consortia have taken these new results and put it through their framework so you can see what happened. And going from the left-hand side of the slide to the right-hand side, you see the impact, which is really quite significant. That you see that from the top plots. The bottom plots are the CP violating parameters in the time-dependent CP violating parameters. And again, you see that is enormously squashed down by the availability of this result, although not no CP violation is seen. Now, if you can just keep in your head the top right plot, I will come back to this finally at the end. Just sort of keep it in your mind, the shape that it is. I'll come back to that. So we mentioned CP violation in CHARM. This can be sought. Well, in the measurement that we've just seen, there's also a similar measurement looking at the KK and pi final states, and one can look for an asymmetry in the effective decay width, or lifetime asymmetry, if you like, by looking at the rate of decay to the KK and pi from either a D or a D0 bar as a function of time. See, so if there's a difference between D0 and D0 bar, that is by definition a CP violating effect. So one again has time-dependent plots, and one is looking for and construct this asymmetry. So if the asymmetry is non-zero, one would see a significant slope here. The data is showing no significant divergence from flatness in these plots, from no difference between D0 and D0 bar, which is at this level of precision, a 10 to the minus 4 is reasonably expected from the standard model, which is predicting this value of delta Y to be in the region of 10 to the minus 5. But LHCb with their high statistics is knocking on the door of being able to examine this down to the standard model prediction in the next era. But CP violation has been observed in CHARM decay. So one can look for direct CP violation. So simply the number of events from D0 bar decaying to KK and pi. There can be a difference in the decay amplitude going to KK and pi. So one can do a very clever method where you do a difference method where you don't just look for the raw CP effect, but you look for a difference in two CP violation effects. And the point being, if CP violation is 0 in both, then the difference is 0. And if you see in the difference a non-zero value, then somewhere there's some CP violation going on, although you don't know in principle whether it is in the KK or pi side at this stage. And this has been seen and published by LHCb in the last 2 years. And the value is there on the screen at the bottom of being 15 plus or minus 3, and so over 5 sigma from 0. This is a well-publicized result, and CP violation is seen in this, what is almost certainly a direct CP violation effect. Okay, onwards. So we have some other direct CP violation effects. These are results from Bell, looking for these are decays which are difficult to reconstruct. D0 going to pi eta, or the DS going to pi eta. These are harder to reconstruct. The CPU violation is certainly not expected in these either, and these analyses find a result consistent with 0, which is completely expected for the statistics involved. An interesting CPU violation search that has been done by both Bell and LHCb is to D to pi 0. So this is a decay which one expects there to be 0, really 0 CPU violating effects because they're in the standard model to very high order, because only one of these two diagrams at the top can contribute in the case of pi 0 by isospin conservation in strong interactions. So this is a good test. The reconstruction level, this is very tricky for LHCb because of what looks like the absence of a vertex. However, the trick is to use conversions in the pi 0 decay. Well, the Darlitz decay, pi 0 going to gamma e plus e minus, which includes a large contribution from conversions in material in order to build up a vertex effectively. Anyway, with the Bell and LHCb results, the world average is now very consistent with 0 at 4 plus or minus 8 cent, as shown at the bottom, or sorry, 10 to the minus 3. Yeah. What's next? Oh yes, let's go on to the B's in the last moments. So there's a long-standing problem with that is known as the decay pi problem. And this has been investigated by both LHCb and now there's a new search has started at Bell 2, and this is something that is going to rumble on through the next decade to be sorted out about what this to resolve this problem. But it's very nice to see that both experiments are looking at this, though admittedly that the progress is going to be dominated by Bell 2 with these sort of Chalmers decays. Moving into the next decade. Finally, unitarity triangle angles.
Malcolm.
Yeah. Yes. So unitarity triangle is a central pillar of heavy flavor physics. There are 3 angles. And I will be talking here about the beta and gamma angles, leaving aside the alpha angle, which there has not been enormous progress, although we do expect this to ramp up with Bell 2 in the future. So the sine 2 beta, one of the beta angles, this is measured famously at the B factories, but now LHCb is really coming to the fore and contributing significantly to the measurement of this angle. And to measure this angle, one is looking at a time-dependent effect. And in these oscillations, here it's the amplitude which is the measurement of sine 2 beta. And so you see this large amplitude, and this is as measured here by LHCb. Taking all the world knowledge together, this is now rather precisely known, and the precision on beta is at the 3% relative level of 22 degrees plus minus 0.7. So yeah, so that's the most precise one. I should mention that that there is this similar mathematics can be applied to the BS system rather than the B0 system. But the difference here is that the CPU violation phase, this beta S is written here, is much smaller with the BS system for good reasons, the standard model, but is pursued heavily not only by LHCb, but also Atlas and CMS contribute here significantly. Because of the presence of the 2 muons from the J psi makes it possible for the GPDs to reconstruct relatively cleanly this mode. The situation is that the world average is now very happily consistent with the standard model, which the standard model is a rather small number, as I say. This analysis will continue into the next decade and greater and greater precision to explore how good this compatibility really is. Last, the analysis of the unitary triangle gamma. So this importantly is something that can be measured in tree level decays with negligible theory theory error through the interference of the two diagrams which are at the top of the page. One is mediated by a beta-U transition and one by a beta-C transition. And the rates of these decays can be relatively similar, and this leads to large direct asymmetries which can be seen in the data, and you can see here in the plot that there is a very, very obvious CP asymmetry in the red peaks, but also indeed in the backgrounds, the blue backgrounds here, which also have similar mathematics behind the scenes. A problem here is that you don't just measure gamma out of these asymmetry measurements, but you also are sensitive to a range of nuisance parameters, RBs, delta Bs, and from the data you've got to extract all of these all at the same time. And you notice here one of the things I highlight is delta D and a delta delta D and RD. So we're once again back to our needing CP conserving phase information from BESS3. And this is done in the K-short pi-pi, K-short KK analysis from in beta DK decays here. And so this is very similar to the charm one we've seen before, except here the three-body charm decay has come from a B. And so once again, we have a binning scheme, we have LHCb data, we have a set of decay rate equations which depend upon gamma and also these strong phases that we measured at BESS3. And from this, because you have all this information, all these separate bins that all have a common gamma value, one can extract gamma with nice precision. This really is the golden mode for getting gamma out for this reason. All this coherent information having to come together to one value. Of course, BESS3, Bell 2 are very much in this game and have recently released a combined analysis using this same mode. The precision there is inferior to that of LHCb, but one expects this to improve significantly over the next decade. This all comes together in a nice combination. This combination is done by LHCb with all their results, the beta decay results and the charm results, all brought together into one combination. And the headline fact is that the value of gamma is now coming out at 65.4 degrees, which is a quite significant shift from where it was prior to this combination, and is now really bang on the expectation from the rest of the sides and angles in the unitarity triangle. And finally, X and Y, in particular, Y receives a bump from this combined method, and the lobe, which I drew your attention to in the charm section, is now reduced even further by including information coming from beta decay decays. And you see the blue loci have now become red and much reduced through this combined information. And so it brings me to my conclusions. A minute or so late, that LHCb is delivering a wealth of measurements on these CPU violation and mixing results due to their large statistics and performance detector. And the summary is that all major results are compatible with the standard model. The search goes on with LHCb upgrade and the advent of Bell 2 over the next decade, and it is no time to be playing football in the park.
Thank you very much, Malcolm, for this very nice and very pedagogical talk. And now it's time for questions. Okay, so I have a question on the binning for the K-short pi-pi. Maybe I was not attentive enough, but I had the feeling that it was not the same binning for this one and for the charm measurement. Can you comment on that? Or maybe I'm wrong, I don't know.
Yes, it's not only a different picture, but it's a different binning scheme. yeah, the one used in the charm analysis is optimized for measuring X.
Okay, so so this different set of optimization then drives me to the so what is, in your view, the next can we do better? Do we what would be the ideal way to optimize? Can we optimize even more in the beginnings? What is the next step?
So
for gamma, I was thinking mostly, but
well, as I mentioned here in the bullet point at the top of this slide, is that the new analysis from BESS3 that came out at the beginning of the year, big pardon, beginning of 2020, gosh, time flies, takes on new data and is done, and the errors on the strong phase information coming through is now small enough that that this will not be a dominant error all the way through the LHCb upgrade era. However, BESS3 has just started taking data again to probably maybe something like a tripling of the data set intended, with more data being taken in the next 2 years. And then this analysis, the strong phase analysis, will be redone with that larger data set, and that will squeeze down the errors even further on the strong phase information come from BESS3, and will that will be sufficient for LHCb upgrade 2 as well.
Okay, so there is still some hope that for the upgrade 2 it's going to be even
yes,
okay.
Absolutely. I think this is being masterminded appropriately.
Okay.
As far as I know, though, the binning scheme, there's already these binning schemes for these specific use cases well designed, and I don't know that that's going to change.
Okay. Thank you very much. Do we have other questions? I do not see raised hands, so I propose that thank you again, and we switch to Alexander Lenz. Okay, can you? Yeah. So okay, yes. So Alexander is going to talk about theory of hadron and CP violation and mixing. So we will have the theoretical context for this. Thank you. So Alexander, so as for Cristina and Malcolm, I will brutally intervene when you will have only 5 minutes left.
That's probably necessary.
Okay.
So thanks a lot. I was asked to talk about theoretical aspects of CP violation and mixing in the quark sector. I will do some general introduction into meson decays and mixing, remind you of the 3 kinds of CP violations, so there's quite some overlap with the talk of Malcolm. And when I want to discuss the status quo of mixing, CP violation and mixing, some comments about CP violation interference, then about direct CP violation, and at the very end I want to come back to CP violation and mixing. Of course, there are much more results when I can discuss, and if you want to see a more comprehensive overview, there's a nice review for the PDG by Tim and Yossi you might want to have a look at. So this is a classification of meson decays according to the theoretical complicatedness. So leptonic decays on the left are most simple. It's just from a QCD point of view, a meson decaying into vacuum, which is described by a decay constant. And you can ask your friends working on the lattice to calculate it for you. Semi-leptonic decays are a little bit more complicated because there's a meson in the initial state and in the final state, which is described by a form factor. This is typically done also on lattice or with like count sum rules. And finally, non-leptonic decays, which are the most complicated ones, where you have to have an additional assumption, so something like factorization, so that this object of having 2 mesons in the final state is actually splitting up in an object which is a form factor and in a decay constant. But keep in mind, so non-leptonic decays are extremely complicated, semi-leptonic decays are very complicated, and you already heard a lot about B anomalies. So B anomalies are typically only covering the leptonic decays like B sub S to mu mu, or the semi-leptonic decays like B to K star mu plus mu minus. Mixing. So in the standard model, you have the possibility that the B meson is transferring into its antiparticle in the anti-B meson, meaning that the physical eigenstates, so the physical eigenstates having a definite mass, like the heavy or the light eigenstate, were actually linear combinations of a B meson defined by the quark content and the anti-B meson. And the coefficients are given up in the red box with a P and a Q. And now we can calculate these diagrams. Calculating the diagrams, you denote them by M12. If you only consider off-shell particles in the loop, you denote it by gamma12. If you consider on-shell particles, so if you would have the charm or the up here. And then you can derive some physical quantities. One physical quantity would be the mass difference, so the mass of the heavy eigenstate minus the mass of the light eigenstate, which is 2 times the modulus of the box diagram where you have only the off-shell contribution. That's, from a theory point of view, the simplest quantity to calculate. A little bit more complicated will be the decay rate difference, so decay rate of the light minus decay rate of the heavy. That's 2 times now the box diagram with on shell, so meaning this diagram where you cut through and where you would have charm or up quarks, times cosine of phi. And phi I didn't mention before, that's the phase of the ratio of the 2 elements of the box diagrams of the virtual and of the real part. And in the standard model with phi is really tiny. So it's a value of something like 1/250. So cosine of phi is very close to 1. Now you can write down the time evolution, which looks a priori very complicated, but in principle, okay, you just have to look at the red quantities. This is delta gamma and delta m, which gives you the oscillation. When all the non-perturbative input is encoded in with blue stuff, and the blue stuff lambda f is the ratio of q over p, this was my mixing coefficients, times the amplitude, A bar normalized to the amplitude A. A bar is the amplitude of an anti-B meson decaying into a final state, and A is the amplitude of a B meson decaying into a final state. So in principle, if you want to describe mixing, you have to know this ratio lambda F, which is a ratio of some non-leptonic decays, which I was saying in the beginning can be very complicated. But there are many cases where the whole in this ratio AF and AF bar are more or less equal, and all the non-hadronic physics is cancelling out, but not always. And finally, we have this pink quantity, which I will define in a moment with the so-called flavor-specific asymmetries. And when you measure it, you get this nice oscillation pattern, which Malcolm was already showing, which was the most recent measurement of delta MS from LHCb. Okay, we have 3 kinds of CP violation. First, we have CP violation in mixing, so where you really consider the difference between the B meson mixing into a B bar versus the B bar mixing into a B meson. Therefore, you're using flavor-specific decays. This is a decay where the B meson cannot decay into the anti-F, so B can only decay into F, and also B bar cannot decay into an F. And in addition, you make the assumption that there is no direct CP violation, so that the anti-B meson decaying into F bar is the same as B decaying into F bar. And then if you calculate, if you insert all these time evolutions, everything will turn out to be very simple. Your lambda Fs, which I had before, are just 0. And in the end, you're just left with this AFS, and in the standard model, this AFS is the ratio of gamma12, that was the on-shell part of the box diagram, normalized to M12, which is a small value in the standard model, something like 5 per mil, times the sine phi, which also was a small value, so something like 1/250. And examples for this decays is typically use semi-leptonic decays, but you also could use this B sub S to ds plus pi minus decay. Naively, you say, okay, I only want to do semi-leptonics because I have a better statistics, but in the very end, I will try to advertise using this hadronic channel. When there's CP violation interference of mixing and decay, where you look at the CP eigenstates, so for example, shape psi phi or shape psi k short, where both the B and the anti-B can decay. And when you have the difference of the anti-B and the B in decaying into the two. And finally, you have really direct CP asymmetries where you have CP violation in the decay. So you compare an anti-B decaying into an anti-F compared to a B decaying into a F. And this we also have seen in the talk of Malcolm when he was, for example, mentioning the B2K pi puzzle or delta ACP. So these are really direct CP asymmetries. Okay, status quo of mixing. When you calculate the mass difference, you need the offshore part of the diagram. You get this expression for M12. So you have some CKM elements. So here VTB, VTS, you have a loop function, the inner-milim function. And when you have this cryptic objects, B times FBQ. So when you calculate the box diagram, you have a 4-quark operator. So you have 2 B quarks, you have a down quark. In the standard model, you have only a vector minus axial vector structure. So you have only one operator appearing here. And in the end, you need the matrix element of this operator, the non-perturbative matrix element. And this is typically parameterized in terms of a back parameter and in terms of decay constants. And this is now by far the dominant uncertainty. So luckily, there was a lot of progress. So there have been many lattice calculations and also many sum rule calculations for this quantity. And this is the first operator with the V minus A structure. And you see most of the results were agreeing very well. With B2, B3, I will come later to that. These are also 4-quark operators, but with different Dirac structures, but they will not arise in delta M, they will arise in delta gamma. For the perturbative corrections, 2-loop calculations have been calculated by Buras Yamin Weiss already in 1990. And I know that Martin Gorban and friends are working on a 3-loop calculation. I was contacting him last week, but unfortunately he didn't reply what's the current status of his calculation, but maybe we get this here, the 3-loop calculation. Now we can compare experiment and theory. So these are the H-fluff averages for the mass difference in the BD and the mass difference in the BS system compared to the experimental numbers. You see roughly they agree. Unfortunately, theory errors are much bigger than experimental errors. So here roughly a factor of 10, here maybe a little bit more. And okay, this is absolutely dominated by this uncertainty in the back parameters and in the decay constants. There was some time ago, there was a small, not anomaly, a small discrepancy. So when we had only the old Fermilab value, which was a little bit higher when it seemed that the standard model prediction is something like 20 inverse picoseconds, which would have had dramatic implications for some BSM models, which are trying to explain the anomalies, but I think this is settled now. HPQCD was updating the numbers, also the lattice, the sum rule numbers are down very close to the experiment, and RBC UK was determining the ratio of BS mixing over BD. So currently I'm only aware that RBC UK QCD together with Shell QCD were updating the numbers to get the individual ones. Okay, maybe this I skip. And when for gamma 1, 2, the structure is a little bit more complicated. So you don't have only one contributions, you have a kind of leading term at dimension 6 contribution, dimension 7. Here you have a perturbative part, so which can be expanded in the strong coupling. And here again, you have matrix elements. Also, the operator for delta M is contributing. This would be my B1, but you have additional operators, and you have operators which have not only 4 quarks, but which have an additional derivative acting there. There was quite some progress. In 2021, partial results for next to leading order corrections to gamma 6 have been published, and hopefully in 22 we will get the full result for gamma 7. I think the biggest improvement that was for the first time 1 over MB matrix elements have been determined on the lattice. So we have quite some sizable uncertainties, but the most important thing is that before you always had to assume vacuum insertion approximation, and now we have for the first time a real non-perturbative proof that this vacuum insertion approximation was working and is what one can do. And comparing experiment and theory, you see that's the theory prediction, something like 0.09. measurement 0.08, theory uncertainty is a factor 2, factor 3 larger. So here this can be improved by all the things which are currently under work, maybe also reducing the uncertainties for Q7, maybe also doing a sum rule calculation for this Q7. For gamma D, the standard model has a prediction has a similar precision. Unfortunately, experimentally, it's not measured yet. And I think the most precise value is still coming from Atlas. So that should be a challenge for my LHCb friends to do something. And this is one of the plots which are typically shown by HFLAF for comparing gamma S, which is the total lifetime of the BS system, to delta gamma S. The green band is typically not drawn in, so this is an addition by myself. If you do only the gray band, when everything seems to be nicely consistent, but if you also include the green theory band, when actually the Atlas value seems to be a little bit off, and I would be very curious to see how this will develop in future. So most of these extractions are done of delta gamma S and gamma S by the decay B sub S to J psi phi. Okay. The next thing is, of course, you can ask about charm mixing. Charm mixing, there are two obvious problems. The strong coupling is larger, so the convergence might be worse. And also for tools like heavy quark expansion, the parameter lambda over MC is at least a factor 3 worse. So it's, of course, a question whether you still can use the tool. But okay, for example, we just did a recent study by discussing total decay rates, lifetime ratios, and in principle, you're more or less getting nicely into the ballpark and almost everywhere touching experiments. So it seems this could work in the charm system. But unfortunately, for demixing, things are becoming much worse. At first sight, you might say, okay, just the same class of diagrams. For B-mixing, I have 9 possibilities. My internal quarks could be up, down, charm down, and so on, up to top, down. And when you have the different topology, so you have to calculate 18 diagrams. If you only look at gamma 1, 2, you only can have internal quarks which can be on shell, so you only have with 4 diagrams. Now you can do the equivalent for demixing, so down, anti-down, internal, down, strange down. So far, everything looks nice. Now you sum up all the terms. Lambda U is always my CKM element. So here it would be VUB, VUS, or VUD, and then the loop function with 2 ups and so on. Next, you use CKM unitarity, and then you get 3 terms. And you have some CKM factors. You can check whether one of the factors is suppressed. And here you have the terms where you see a Chim constellation. So for example, here you have 2 charm quarks, 1 charm quark, no charm quark. If all quarks would have the same mass, then all these terms in the square brackets would add up to 0. So now you have to look at 2 things. You have to look at the size of the CKM elements. For example, for PS mixing, lambda U is suppressed. So this first one is the smallest term, second smallest, this is the largest. And then you have to look at the loop functions. The loop functions go like the internal mass squared divided by the W mass squared. So for example, here you have tops. This will be a large number, 4.5. MC is already small, less than 0.2 per mil. And mu is more or less exactly 0. So in principle here, only the top is surviving. Here 2 tops, here 1 top. The charm can be set to 0, and this you can nicely forget. Now, if you look at the charm sector, unfortunately, things are different, because this lambda B, where you have the less Chim suppression, is by far, so it's crazy CKM suppressed. It's Wolfenstein parameter to the 12. So here you're always multiplying. Either the CKM structure is large when Chim is extremely pronounced, or CKM is small and when Chim is less pronounced. So that's the problem with charm mixing. And therefore charm mixing, okay, but now it's measured quite precisely. We have seen the new result. And if you do a naive application of these tools, of these heavy quark expansion tools, when you get values which are 4 or 5 orders of magnitude below the experimental number. And the question is, where is this coming from? You also can use different tools like exclusive approaches, but unfortunately, we don't have currently a real first principle calculation. But still going a little bit back to the mixing, In the inclusive approach, so the interesting thing is if you calculate only one diagram, then actually you get the result which is larger than experiments. So it's not that the heavy quark expansion itself is producing small numbers. It's only when you calculate with extreme Chim constellations of this combination of the terms that you get with small numbers. And there have been several solutions in the literature where this might come from. One is you might have duality violations, but the nice thing is you don't need duality violation on the scale of 10 to the 4 or 10 to the 5. You just need 20%. So you say you calculate the charm decay and you have some 20% of duality violation, and that's already sufficient. So because when the Chim constellation is not effective anymore to produce that. There were some ideas that this is coming from higher orders in the heavy quark expansion where Chim is not so suppressed. Another idea what we recently had is, so you have with contributions with internal strange quarks or internal strange and down quarks, and everybody was always using exactly the same renormalization scale. And in principle, these are different objects. The one is a delta S is equals to 0 transition. The other is a delta S equals to 1 transition. So you're not forced to set the renormalization scale equal, and actually setting them equal implicitly assumes, because the Chim constellation is so pronounced, a precision of 10 to the minus 5, which is of course not the case. And if you just give up with assumptions, there were different ways of doing it, either just varying the scales independently for the diagrams or introducing, saying the SS diagram is differently affected when the DD diagram, where for introducing this epsilon, when you also can cover the experimental range. But in principle, it just tells you that the uncertainty of the inclusive approach is also larger. But anyway, so this is, I think, a promising statement that both exclusive and inclusive approaches can cover the experimental regions. On the other hand, the bad thing is, I think, both approaches do currently not allow for a real precision determination. Okay, CP violation in mixing with AFS was equal to the imaginary part of gamma12 over M12. Now, you simply could calculate gamma12 over M12, or you massage it a little bit, so you use CKM unitarity, and then you can write this expansion. So you get the leading term, which is gamma12 over M12, where you have all the CKM elements were cancelling. You have no Chim suppression. Also, you have no imaginary part, so this will not give you a contribution to the semi-leptonic decays. It's small, something like 5 per mil, and this is the overall contribution to delta gamma. So delta gamma over delta M is the real part of this. When you have the red contribution, where you have now a CKM element lambda U over lambda T, which has an imaginary part, and you have here a Chim suppressed term. And you have the green part, which okay, you be included for numerics, but in principle, it's irrelevant both for delta gamma and both for alpha S. If you do the standard model predictions now for the semi-leptonics in the S system, you get something like 2 times 10 to the minus 5. In the D system, you get something like 10 to the minus 4. So tiny, small numbers. I don't remember when HFluff was last updating, so I just was guessing this year number. It's quite some time ago, and I hope soon my friends will update this value. Okay, the next CP violation is CP violation in interference. When you calculate with time evolutions, you insert everything. Again, everything depends on these ratios lambda F. Now, if you make the assumption that only one topology is contributing to the decay, so for example, you have B sub S to J psi phi, we have a tree-level topology, and you say you neglect the penguins. If you do that, when in this ratio, all the non-perturbative things are cancelling out, and you're just left with the CKM phases. So in that case, you have this golden-plated mode, which is nice. Now, as soon as you have two topologies, so if you say you have a tree-level topology plus a penguin, so this could be a standard model penguin, it could be a BSM effect, when this ratio is again with CKM stuff plus a 1, and when corrections which go like this value R, and R is the value of the non-perturbative penguin amplitude normalized to the tree amplitude. So now, in order to really make a precise statement, you have to know this value of R. And I already told you, non-perturbative decays are extremely difficult. So therefore, people are trying different things like symmetry relations. So where Robert did a lot of things. I think I'm only one paper I'm aware of where people were doing QCD factorization. This was the last one by Uli Nierste and friends. But anyway, I think there's a kind of consensus that this penguins will lead to an uncertainty of something like ±1 degree. Therefore, also was modifying this H-fluff plot for showing the phi s versus delta gamma s ratio, because typically people just quote the CKM fit or UT fit value and say this is the standard model. This is not the standard model. This is the standard model if you assume penguins are not present, but we know they are present in the standard model. As soon as you assume it, you would have to get this bigger wide range. Okay, next we have direct CP violation. If I calculate this ratio, the time evolutions, insert everything. When I see my whole asymmetry, the leading contribution to the asymmetry is now with R, with ratio of either penguin over 3 or one of new physics over 3. So for mixing induced, R was a correction. Now R is the dominant effect. Therefore, direct CP violation is extremely hard to predict.
So 5 minutes.
And now something which at first sight is unrelated. So we could look at non-leptonic decays and describe it by theory. And the simplest non-leptonic decays are the so-called color-allowed tree-level decays, like B sub s, ds plus, pi minus. You can make your QCD factorization prediction and you can compare it with experiment. And when you get this nice table, which Nicole was producing, and you see deviations between 3 and 7 sigma. Okay, now if you see such a thing and you don't know what to do, you put a poll on Twitter and you ask the Twitter community, what do I think, where is this discrepancy rooting in? And my friends they are very keen on experiment because nobody said anything was going wrong in experiment. They don't like QCD factorization because 90% said it might be a problem there. And 9% are considering new physics. So there's quite some work going on. I listed some of the papers here, what people are discussing. And another thing one should keep in mind, as soon as you have new physics in this tree-level decays, also the extraction of the CKM angle gamma might become more interesting, because in the standard model, this is extremely precise. But if you allow new physics in non-leptonic decays, you actually might modify the determination of gamma by several degrees. So unfortunately now the gamma angle is really sitting spot on the CKM theta value, but some time ago when it was 5 degrees off, that looked quite interesting. Okay, and that's also therefore I don't have to say really something new about the B2K pi puzzle or about delta ACP. People are still arguing whether it's standard model or not, so you can find different discussions in the literature. But I would like to conclude. So in principle, it was a little bit pessimistic. Everything is super complicated. We cannot really say something, but I want to give you a nice take-home message. So with semi-leptonic, with flavor-specific asymmetries are typically measured with semi-leptonic decays. These are the old ancient H-fluff values, which hopefully will soon be updated. Now you also could think about using this flavor-specific decay. Why? First of all, you have some experience, you use it for delta ms, and next there might be some discrepancy. So if there is new physics, when with B sub s to ds plus pi minus in the standard model would not have only the tree-level decay, but also a new physics contribution, which in principle could also be CP violating. If QCD factorization and the error estimate is correct, then this value of R should be between 0.1 and 0.2. Now you again can calculate the time evolution. Now the result will be a little bit more complicated because you allow for direct CP violation. And to a good approximation, you would expect this to be with AFS, which is the imaginary part of gamma 1, 2, minus the real direct CP violation stemming from new physics. And if this R, as indicated, is up to 0.2, then this asymmetry could be up to 40%. So now if experiment is on the one hand measuring the green with semi-leptonic decays more precisely, measuring red or with AFS, also with a high precision. And if you find a significant discrepancy with the two numbers, you have an unambiguous signal for some BSM effect independent of any theory input. Thanks a lot.
Thank you very much, Alex, for this very nice talk and giving us some hope of things we can do. So I see Malcolm raising his hand.
Yeah, can I bring you back to the phi-s plot and the apparent broadening of the white line? So that would seem to be quite an important message. Can I ask? Is there a chance that that broadening might be reduced through some complementary measurement?
Well, there are many things in the literature. So, okay. The one is to have some control measurements. So there's a big list, unfortunately I don't have it in my head, of making some control measurements. So you have decays where you expect the ratio of tree over penguin to behave differently. And this, if you have a big bunch of these decays, when you could get an indication how big is the penguin compared to the tree amplitude. When this, so I started, in principle, all these papers I had here, which is only a small part of literature which is discussing with penguin pollution. So most of the current ways how to approach it, where you're using things like SU3 flavor symmetry, which is of course not a bad idea, but at some point I think we are reaching the limit of this method. So this last paper was the first one who tried to use purely theory methods, but again, so we somehow will reach a wall currently at 1 degree. So I could not give you an exact number. So how probable is it to reach plus minus 0.5 degrees or plus minus 0.3 degrees? For sure, there is progress possible, but I think it's a very slow one. So currently, okay, I did here by hand, I did plus minus 1 degree. And I think this is not far from the current truth. Of course, it's important for you because you put a lot of effort in reducing phi-s. But as soon as you're smaller than this uncertainty, the ball is really in the theory's corner.
Thank you.
I do not see other raised hands. So thank you very much. And we will move to the last talk of this session, which will be given by Xiaoyan Shen on highlights in baryon decays. Xiaoyan, yeah, okay.
Yes.
Yes, we can see your screen now.
Yeah.
And as for the other speaker, I will indicate you when you will have only 5 minutes left.
Okay.
Thank you.
Okay, thanks for the invitation. And I think I should turn on my video. Yeah. Okay. Okay. Thanks for the invitation for presenting this the highlights in baryon decay. And so this is a quite big topic of this talk, but I think I will only focus on the test of CP violation from the hadron decays and also from the charm baryon and the beauty baryon decays. And I will also talk about the flavor change neutral current processes in these decays, and also the lepton flavor universality test from these decays. And finally, I will give a short summary. And I apologize for probably we're missing many important results. So as already mentioned in the previous talks, and we know CP violation plays an important role to explain the dominance of matter over antimatter in the universe. And we have already heard that in the Standard model, CP violation can be measured in 3 different ways. and directly in the decay or indirectly in mixing or in the interference between the decays with and without mixing. And the CP violation has already been observed in the meson sector. Like in the many years ago, in 1964, the CP violation in Xiaoyan sector was discovered. And then about 20 years ago, the CP violation was discovered in the beauty sector. And 2 years ago, and very recently, RHCB discovered the CP violation in direct charm decays. However, the amount of CP violation observed is still too small to account for this matter and antimatter asymmetry in the universe. And another thing is the CP violation in baryon sector has never been observed. So it gives us a good opportunity and a lab to try to search for the CP violation in the baryon decays. And for the Fourier change in neutron current processes, this kind of decays are extremely suppressed because of these cannot occur at the tree level and only arise at the loop level, and also it's further suppressed by the gene mechanism. So if we can observe the FCNC's process, this will be a good probe of new physics beyond the standard model. So now, so the results in this talk mainly from the Bayer experiment and RHCB experiment and also BAS3 experiment. And we know Bayer experiment, they have totally about 980 inverse Fendbar data on the upstream peaks or off peak or scan data. And so for the RHCB, and it's a PP collision experiment at 7 or 8 or 13 TeV. And this is the experiment dedicated to the heavy flavor physics. And the BAS3 detector is sitting at electron-positron collider, and the collision energy is at from 2 to 4.9 GeV, and this is a detector dedicated to torsion physics. So most of the results I'm talking about will be only focused on these experiments. So the first thing is I will try to introduce you the hadron physics. So I will not talk about the hadron structure and only focus on the decay of hadron. So hadron is any baryon containing one or more S quarks, but no charm or beauty or top quark. So if we replace one of the light quarks in the proton with one or more S quarks, then we have these hadrons like lambda, sigma, cascade, or omega. So there are three kinds of decays for the hadron. It's non-leptonic weak decay, or semi-leptonic decay, or the weak radiative decay. So for the hadron non-leptonic decay, the parity violation in hadron decay was predicted by Li and Yang in 1957. And for example, for this kind of process, the hadron decays to an octet baryon plus a pion. And the final state will have the S wave, it's a parity violating process, and P wave parity conserving process. And there are three decay parameters, alpha, beta, and gamma. And among them, only two of them are independent. So for example, this is alpha and beta and gamma, the definition of them. And so if the hadron state has a non-zero polarization, and then we can have this kind of the distribution. And so if CP is conserved, and then the decay parameters for the hypron and the anti-hypron are equal in the magnitude but opposite in sign. So if CP is a symmetry, then we can measure these ACP and BCP to test the CP. So at batch 3, the hyprons and the anti-hyprons are produced entangled and polarized. So because of the large branching fraction, so if we have a large statistic data of, for example, the charmonium state like gypsy or cypron, then we can have, this will bring us a large statistic of lambda pair or sigma pair or cascade pair. So because of the parity conservation in the charmonium decay, so the produced lambda or lambda bar or sigma bar are polarized. They are transverse polarized. So this will bring us many benefits for us to test CP. So here is a formalism for example, for the E plus E minus goes to hypron, anti-hypron pair, and then the hypron goes to a baryon and a meson. And so all the results I will report here will be based on this formalism. This is in the reference. So this is the alpha minus and alpha plus or an ACP results listed in the PDG 2018. So you can see there are lots of early experiments measured especially alpha plus and also the alpha minus. And at batch 3, in 2 years ago, based on the 1.3 billion gypsy events, we have analyzed gypsy goes to lambda bar, and we try to measure the weak decay parameters and perform the CP test from the lambda decay. So the upper 2 plots shows you the lambda signal. I just want to give you an idea that you can see the background level is very low. It's almost free of background, and we have very clean sample. So for the first time, we measured the hypron polarization at gypsy, and we found the lambda is transverse polarized. And so this non-zero delta phi allows us for the individual determination of the lambda and the lambda decay parameters. And then we can use this lambda and the lambda bar decay parameters to determine the CP asymmetry parameter. And we found that this alpha minus value is about 7 sigma shift from the PDG 2018 average. So this yellow band shows you the PDG 2018 bands. We can see our measurement is far away from this band. And but our result is this is the most sensitive test and of the CP violation for the lambda hypron. And after this result, the people use the class Xiaoyan photon production data to reanalyze this Xiaoyan photon production data and measured the lambda decay parameter alpha minus. And so from this process, they found that alpha minus is about 0.721, which is quite close to batch 3's results. And then recently, based on 10 billion gypsy, which is about 7 times of our previous data sample, we updated our results for the lambda decay parameters. So you can see here are the results based on the 10 billion gypsy, and these are the results based on the previous 1.3 billion gypsy. So here you can see this green band is for the PDG 2018, and this the yellow band is for the PDG 2021. And our updated value is right here, is about 3 sigma away from the PDG 2021 band. And but with the most precise, the precision measurement. And this is for the alpha plus. And also the error is quite small. And here is a CP asymmetry from these two numbers. So then how about the sigma case? So here I will show you the CP test in the sigma goes to p pi 0 and the p bar pi 0 based on the 1.3 billion GIP psi and the 0.4 billion psi prime data. And again, this is almost free of background. It's very clean. So we can, this is the distribution for the GIP psi case, and here is the distribution for the psi prime case. From the fit, we can obtain the alpha GIP psi and alpha psi prime, and also we can obtain the decay parameters. With these decay parameters, we obtain the CP asymmetry from this sigma for this sigma, and which is consistent within the standard model prediction. And so this is, and also this is the first CP measurement for sigma decay. And then how about the cascade case? So because we have for the cascade, it decays to lambda pi, and then lambda goes to p pi. So this is a sequential decay process, and the situation is more complicated, but this decay can completely be described by two independent parameters, alpha and phi. So CP violation can be quantified in terms of the ACP and also the delta phi. So so one advantage in this decay is for the ACP, this is roughly equals to the related to the strong phase difference of the final state interaction. This term is quite small, and then it's also related to the weak phase difference. And on the other hand, we can try to measure this delta phi CP, and this delta phi CP in the leading order is only related to the weak phase difference, because this strong phase difference is small. So this delta phi CP is more sensitive for the CP test compared with this ACP. And so the polarized cascade beams are very helpful for us to measure this delta CP. And the precision for this measurement is limited by the magnitude of the polarization and also the accuracy of the polarization determination. And here I will just show you some results. Again, we can see this is a cascade signal, and here from the scatter plot, we can see very clear signal region here, and with a very low background. And so with this fit, we finally obtained all these decay parameters. Firstly, we first measured the polarization of this delta phi value. And then we direct measured all the decay parameters. So for example, the alpha cascade bar, and the phi cascade bar, and also the alpha lambda and alpha lambda bar. So this is the independent measurement of the decay parameter, which are in good agreement with our previous batch 3 results based on GIP cycles to lambda lambda bar. Even though here the statistic is about 6 times lower than our previous example. The reason is here we have the sequential decay, so we can use more information here for the in the fit. And also the very important thing is we measure the 3 independent CP symmetry parameters in single channels. So these are the results compared with the previous results, and many of them are the first measurement. So for the hadron decays, so we have, up to now, we have already measured the most precise CP, performed the most precise CP test from the hadron decays. And also from the hadron semi-leptonic decays, we can use this to test the lepton flavor universality. So this is the first absolute branching fraction measurement. Lambda goes to P mu nu. And so here you can see, compared with the other experiment, our result is the most precise one. And from the test of the lepton flavor universality, the result is consistent with the standard model prediction. And the battery also use this to measure this ACP, and this is consistent with the CP symmetry. And the form factor measurement via the lambda goes to PE nu is on the way. This can be used to extract the CKM matrix BUS. So for the weak radiative hadron decays, lambda goes to N gamma. This actually, there are some experiments measured this kind of decays, but their values are differed by 2 sigma. And here, batch 3 measured this with the 10 billion gypsy events. Gypsy goes to lambda, lambda bar, and they measured this, the branching fraction of lambda goes to N gamma, and lambda bar goes to N bar gamma. You can see that the current batch 3 results are away from this PDG average value, about 5.5 sigma. And no CP asymmetry is found here from this decay. So for the charm baryon and for the beauty baryon decays, so I will mainly talk about the semi-leptonic decays and hadronic weak decays, as well as for the beauty baryon decays, I will show you the results for the weak radiative decay. So a couple of years ago, batch 3 have measured the absolute branching fractions for the lambda C decays to lambda and the semi-leptonic decays to lambda, lepton and nu. And this is the result for lambda E nu, and here is the result for the lambda mu nu. And with these results, the lepton flavor universality can be tested, and it agrees with the standard model expectation. And also with this absolute measurement of the semi-leptonic decays, these have already been the important input for the lattice QCD's calculation. This is a lattice QCD's calculation for this semi-leptonic decay. So right now we can see that in the batch 3 results, the statistic error is dominated. So at the moment, another about 4 inverse lambda data is already collected near the threshold. So the more precise results can be expected in the near future. And for the band, also measured this, try to measure this omega C semi-leptonic decay to test the lepton flavor universality. And this decay was first observed by a CLIO experiment, but with very low statistics. And with spare data, they have used the omega C goes to omega pi as the reference mode, and this is for the electron case, and here is for the muon case. And so they measured the branching fraction of this lepton case to the pion, the reference case, and then they test the lepton flavor universality, and they found this value agrees with the expectation of the lepton flavor universality. And these branching ratios can be used to compare with the theoretical calculations. And Baer also tried to study this cascade C decay, semi-leptonic decays to test the lepton flavor universality and to measure the CP asymmetry parameter in this hadronic decay. And this semi-leptonic decay was first observed by the August experiment with very low statistics, and further confirmed by Creo experiment. And
Aufstehen, Sammy. Nicht schlimm, nicht schlimm, alles okay.
I'm sorry. Okay. So here, Baer experiment observed these semi-leptonic decays, and also they have tried to do the CP test, and they found that they derived the decay parameters and have measured the CP asymmetry parameter. And I listed these results here, and the decay parameters, the precision of this is much improved, and the CP asymmetry parameters tell us that these are agree with the CP conserved. And for the
5 minutes left, sorry.
Okay, so for the lepton flavor universality, they found that this is this value, this ratio agree with the expectation of the lepton flavor universality. And the BEST3 also tried to study this lambda C decay asymmetry measurement in entangled lambda C pairs. So they only used about 0.6 inverse Fendt data. So right now the statistics is still dominate. So they are trying to analyze the more data which have already been collected. So the more can be expected in the near future. So Baer and BEST3 observed singly Cabibbo suppressed decays. So I will just list this here and will not talk about the details. So for the beauty baryon decays, so this is a very new result from LHC-B, and they have just posted the result today, I think. They made the first observation of the lambda B semi-leptonic decay to lambda C plus tau nu. And so the reference mode is lambda B goes to lambda C and 3 pi, and the tau is reconstructed from the to the 3 pi. So the signal yield is measured by a 3-dimensional fit, and then for the first time, LCB observed this semi-leptonic decay with the about 6 sigma statistical significance. So they measured the branching fraction of this decay, and they also get the ratio of these two decays to test the lepton flavor violation, and which is in agreement with the standard model prediction. And the B to S gamma transition is a flavor change neutral current process is forbidden at the tree level. And in this case, the photons are dominantly left-handed, and the right-handed contribution are suppressed. So if there is a large right-handed polarization, this could be an indication of the physics beyond standard model. So in the meson case, this B to S gamma transition have been indirectly studied by the Baba, Bear, and LHCb, and they didn't provide the string constraint on the presence of the right-handed contribution to this B2S gamma process. And then what's the case in the baryon decays? So 2 years ago, LHCb made the first observation of lambda B goes to lambda. So experimentally, it's very challenging, and but they made it with a statistical significance of about 5.6 sigma. And they measured the branching fraction of the lambda B goes to lambda. This result is in good agreement with the theoretical prediction. And recently, LHC made the measurement of the photon polarization in this lambda B goes to gamma lambda. And so this is the result with 6 inverse Fentiba data. It's much larger statistics compared with the results 2 years ago. And also they can measure this this distribution to fit this distribution to measure this the alpha gamma and the product of alpha gamma and alpha lambda. And the TechBest3's results on alpha lambda, and they can obtain the photon polarization alpha gamma. This result agrees with the Shen model prediction. And so if they separate the data to the lambda B goes to gamma lambda and the lambda B bar goes to gamma lambda bar, and they can measure the gamma alpha gamma and alpha gamma minus and alpha gamma plus separately. And with these values, this is consistent with the CP symmetry. So you can see the current results are dominated by the statistical uncertainty. So more can be expected in the future with more statistics. So and LHCb also tried to search for the radiative decay of cascade B goes to gamma cascade. So they didn't see the signal, and they just set the upper limit here. And for the study of the lambda B goes to dpk, this can be used to study the CP violation. For example, for the lambda B goes to dpk is suppressed, and compared with this lambda B goes to dpk minus. And if we use the so the interference of the following 2 amplitudes is related to the secant angle gamma. So the gamma can be extracted, but the difficulty is this is very complicated because of the lambda B and also the proton. But this is provide a way for the LHCb to extract gamma anyway. So here are the results from the measurement. So they have used the 9 inverse Fentiba data to measure these decay branching fraction, the decay branching fractions in the different phase space region. And so this kind of the suppressed decay is observed for the first time. So if with the large statistics, the secant angle gamma can be extracted.
1 minute left, Xiaoyan.
Okay, so finally, so we have already known that the entangled hyperon-anti-hyperon pairs produced from the charmonium decays open a new area to search for the CP violation. So we have already had the most sensitive test of CP violation for the lambda, sigma, and the cascade. And more tests on the lepton flavor universality from charmed baryon decays at Bayer have been performed, but no violation observed. And the threshold and entangled production of lambda C pairs also provide us a good opportunity to test the lepton flavor universality and CP violation. And recently, LHCb made the first new observation of the lambda B semi-leptonic decays, and the ratio of these semi-leptonic decays is in good agreement with the standard model. The lepton flavor violation is not observed here. And LHCb also measured the angle, the photon polarization from the lambda B goes to gamma lambda. This is in agreement with the standard model calculation, but the statistical uncertainty dominates the full analysis. So the more can be expected in future. So that's all for my talk. Thanks for your attention.
Thank you very much, Xiaoyan. I'm sorry I'm back again. I had some network issues at home. So thank you very much for this very comprehensive talks. Do we have questions? I'm connected on my cell phone, so it's not easy to see if there are raised hands.
Yes, we are.
So
Malcolm, go ahead.
Okay, can I just have a quick clarification, please, on the lepton flavor universality test with hyperons? On slide 19, you had it on slide 19. This is a very simple question, but I was quite surprised to see the standard model calculation to be so far from 1. That's purely due to the mass difference of the muon and the electron, is it, or is there anything else going on?
Yeah, so this, so actually I don't know. So any theorist can answer this question for this standard model calculation for this value.
I mean, clearly I can look at the paper. I just
actually in many cases it's like in the charm decays. If we test the semi-leptonic decays, we can see lots of them actually are not really 1 because of the different mass or different
Yes, I mean, you talk about the charm baryons later on, and they seem to be pretty, 1, let's call it. But okay,
yeah,
this hyperon's
this
lower in mass, is less phase space. I'm just a bit surprised that it's so far away from 1. But yeah, I will look at the paper. Thank you.
Yeah. Okay. So Marco.
I had a quick question on slide 13. It's fantastic to see this update with a full data set of this alpha minus parameter. Can you say a little bit more about this 3 sigma tension to the class result, or did they comment on the already somewhat smaller tension to your previous result?
So actually, our results are consistent with our previous results, but with with a much improved precision, and not only for the statistics but also for the systematic, because we so for the control sample we have used because of this huge statistics and the the control sample we use to estimate the systematic uncertainty is also become large. So that's why the systematic uncertainties is also reduced. And in terms of the class data, so actually the class data is already so actually I don't know why. Still have this about 3 sigma difference, yeah, away from the class calculation, away from the class measurement, yeah. So actually this is the remeasurement, reanalyze of their data. So Actually, I don't know the details of their analysis.
Okay, thank you. Maybe also a case of looking at their paper. I was just wondering whether you were aware of any comments they might have made about the general situation. Anyway, very good to see this update. Thanks very much.
Okay, thank you. Do we have other hands? I'm still blind.
I don't see any.
Okay, so thank you very much, Xiaoyan, and I would like to thank the 4 speakers for this very nice and a very nice presentation. And in particular for also having kept their time despite the wide ranges of the topics they have to deal with. So thank you, very nice. And now I give back the hand to Marco.
Thanks very much, Marie-Hélène, for chairing this session, for battling through your connection issues there, and to all speakers for their talks. I would like to point you to the poster session that will start in just over 5 minutes now. I just posted the latest overview slides with all the links and indications of who's presenting their poster today. So please connect, discuss the posters, and vote for your favorite. I'm told there've been a fair few votes already following yesterday's session, so please make sure we've got a good idea of who are the best presenters. I connected yesterday to several of them, and they were fantastic. So I'm looking forward to a few more today. So thanks very much. We will then reconnect in the afternoon for our parallel sessions that will also continue tomorrow morning, and we'll reconvene in plenary mode in the afternoon tomorrow. Thanks very much. Bye-bye.
Bye-bye.
Bye, everyone.